map computations. And I'll describe what I mean by that in just a second. So the main problem that I'm considering is a problem that we've seen several times already during this workshop, and it's the problem of shape correspondence or shape matching. And the idea is that given a pair of shapes m and n, we would like to somehow find correspondences between points that are defined on these shapes. And there are several versions, so we can either look at correspondences between some landmark points or maybe dense correspondences between all points. Okay? And of course, probably for this kind of audience, I don't need to motivate this problem, but just to provide a sort of a reason for why we study it. One of the kind of main reasons why you would want correspondences is essentially it allows to transfer information from one domain to the other. So if you have a pair of shapes and you have a texture or parameterization, you can transfer it from one shape to the other. Similarly, if you segment or if you have some labels on one of the shapes, you can transfer it onto the other if you have correspondences. And finally, if you have, for example, deformation or you have animations, you can also transfer them, which is kind of a big problem in computer graphics. And in all of these applications, I mean, there are many others, but in all of these applications, you really need to concentrate on this ability of correspondences to transfer information. Okay? So for the purposes of my talk, just to kind of specify what I mean by shapes, basically I'll be talking about discrete triangle meshes, and these, so basically just to give an example of kinds of shapes that we have in standard benchmarks. So these are triangle meshes. So basically it's a collection of points and triangles, and the complexity is between, let's say, 5,000 and 200,000 triangles. So this is important in a sense that anything that you want to do that requires, let's say, quadratic complexities is already prohibitive on these types of shapes. Okay. I also typically assume that these are manifold without boundary and so on, but these are slightly more technical assumptions that you can often lift with appropriate boundary conditions, for example. So basically my talk is about functional maps, and this is something that, as I mentioned, we saw, we saw yesterday. And the idea, just to kind of recap, is the following. So suppose I have a pair of shapes m and n, and I have a correspondence t, so a mapping that takes points on n to points on m. So the direction here is slightly important, so I specify it with this arrow. And this correspondence between points induces a mapping between functions via pullback. So if I have a function defined on m, so a real valued function defined on m, I can use this mapping t to define a corresponding real valued function defined on n by just borrowing the values. So for every point on n, I just look where it maps. I take basically the value of this f, and that gives me a transformation. Okay? And this mapping between functions has certain nice properties that are really important for us. So the first property is that it's linear. So linear basically means if I take a linear combination of two real valued functions, then the image of this linear combination is also a linear combination of the images. And this is just a trivial consequence of the property of pullback, right? We're just basically borrowing values, so it's not even a theorem or anything. The other thing is that it's complete in the following sense. So if I give you kind of, so suppose that I know some transformation between real valued functions, so I'm denoting it by t sub f, but, and I know that this t sub f comes from some correspondence t, but I'm not telling you which one. So let's say I give you an oracle that allows you to transfer functions from one shape to the other, and your goal is to basically recover this t that it came from. Basically, I claim that it's possible, so this is this property that I call completeness. And one thing that you can do, for example, is just feed to this oracle highly peaked functions around certain points. So for every point on shape m, you can basically construct something like a delta function, try to transfer it using this t sub f, look at the image and take, for example, the local maximum, and that gives you the corresponding point for this point on m. Okay? There, of course, you can do it even in a simpler way, for example, by transferring the x, y, z coordinates using this t sub f. Okay? And now we make a slightly stronger assumption, which is the following. So suppose that both f and its image live in some appropriate functional space. So for today's talk, I'll assume that they both live in the Sobolev space H1, but the exact space that is appropriate for this kind of functional map framework, I think is still an interesting question that we can discuss. But essentially the main thing that we would like is that both f and g, so both the original function and its transferred version, have to be expressible in terms of some basis function. So we basically want the space to admit some kind of a basis decomposition. So I have a set of basis functions phi sub I on M, and I also have some set of basis functions phi sub j on n, and I basically try to express f and its image by a linear combination of these basis functions. And since we know that this transformation t sub f that takes real valued functions from the source onto the target is linear, and since we know that this both f and g can be expressed as a linear combination of these basis functions, this essentially implies that there is a linear transformation from the set of coefficients ai to the set of coefficients bj, right? And this is precisely what we're going to call this functional map. It's basically just a linear transformation that takes coefficients in one basis and transforms them into coefficients in the other basis, and we know that it has to be linear, right? So this is a very, very basic observation, but this is kind of the basis of everything I'm going to be talking about later. So for the basis, traditionally, or at least commonly in this domain, we use the Laplace-Beltrami eigenfunctions that also came up yesterday. So basically, these are solutions to this eigen problem, where basically we have the Laplace-Beltrami operator defined on the surface, and there exists several classical discretization for it. And we're looking for the functions that basically solve this eigen problem, and they have certain nice properties. So just to mention two, so first they minimize Dirichlet energy, so basically we take the first k eigenfunctions, and these are precisely the functions that are somehow smoothest, as smooth as possible. And so what we mean by smooth here is basically functions that minimize this integral of the squared norm of the gradient, right? And that's precisely the eigenvalue of the corresponding eigenfunction. And so, so that's kind of the nice thing, is that they have the smoothness, which gives us also a notion of scale. So we say basically frequency or smoothness corresponds to scale. And here we also the fact that they're ordered, so these eigenfunctions are ordered by the eigenvalues, allows us to say what we mean by the first k, for example, basis function. Okay. All right. So kind of putting all of this together. So I said that basically for every mapping, so for every correspondence between a pair of shapes, we can represent it as a linear transformation between functions. We can be encoded through some matrix C for a given choice of basis on the functional spaces. And I think this kind of image that maybe we saw a variation of yesterday, I think it's quite helpful. So basically we have some basis shape M, and we have a function. So here the function is just encoded by the color. So it may be 0 on most of the body, and it's close to 1 on one of the feet. And we represent it as a linear combination of some basis functions. And we also have this transformation that allows us to transform these functions, so this t sub f. And this transformation can be expressed as basically, so first we take this function f and we represent it in the basis on M. So this is this phi pseudo-inverse on M. Then we transport the coefficients using the C, and then we reconstruct the function on the shape N using the basis on N. And this matrix C is precisely this functional map matrix. Okay. So this functional map is basically just the matrix C that translates coefficients from one basis to the other. It's kind of a very simple idea, actually. Okay. So just to give you sort of an example of the size or the complexity of these kinds of matrices. So in this plot, we show on the x-axis the number of basis functions, the number of Laplace-Beltrami eigenfunctions that we use for representing this matrix. And on the y-axis, we basically show the reconstruction error. So I have a few pairs of shapes, and I have correspondences between them that are encoded by the color. And these are kind of the natural correspondences that you would expect. So the right paw of one cat corresponds to the right paw of the corresponding cat. So it's basically the sort of the natural correspondences. So we have these pointwise correspondences. We encode them as these matrices of size k by k, where k is the x-axis. And then we try to recover the correspondence by basically using this approach that I just mentioned, by feeding to this functional map these delta functions. And on the y-axis, I'm plotting the error that I get when I'm doing this kind of this conversion. And the scale of the y-axis is not that important, but here you can see that basically around 80 or so basis functions, so these matrices of size 80 by 80, we can reconstruct the point-to-point map with an error of less than 1 edge length of the mesh. And these are meshes of approximately 28,000 vertices. So instead of representing a correspondence as a 28 by 28,000 matrix, we represent it as an 80 by 80 matrix, and that allows us to encode the correspondence with basically an error that's less than 1 edge length of the mesh, which is kind of acceptable in many applications. And this is really important because it allows us to basically do this processing in a much more reduced space. And I think this is where a lot of the sort of advantages computationally come from. All right? So now, you know, the original motivation was I have a pair of shapes and I'd like to, so in the previous slide we saw how to recover a given point-to-point correspondence from, you know, by translating it into the functional map and then recovering back. But in practice, we're interested in a different problem, which is I give you a pair of shapes and I would like to find the correspondences between them, right? So this is the problem that I'm trying to solve. So one question is, how can we use this functional representation to compute the maps in practice? Something that basically, this is a kind of basic pipeline that that we proposed a few years ago. It has the following simple observation. So suppose that I don't know this functional map matrix C. So this is what I'm trying to solve. But often I can write down some constraints, some basically pairs of functions that I would expect C to preserve, right? So for example, the Gaussian curvature is a function on the surface of the mesh, and I can encode it in a basis. And the same thing for the Gaussian curvature on this target shape. And I can encode both of these functions in some basis through their coefficients. So this is A and B. And so basically I would like to find a C that I don't know, but if I did know, I would expect the C to approximately preserve this quantity. So these quantities we typically call descriptors or features, right? So Gaussian curvature would be one example of a descriptor. Oh, sorry. Yeah, of course, yeah, there's a good question of what are good descriptors that actually, well, we can discuss. But the key part here is that essentially, given enough pairs of A and B, given enough of those kinds of features, you can recover this matrix C by just solving a linear system of equations, right? So this is, in some sense, very convenient because if you have a set of good descriptors, you just basically invert this linear system and you get a good matrix C, okay? So this is the kind of pipeline that we propose. So essentially, the way it works is like this. So I have a pair of shapes. I'm trying to find a correspondence between them. So first, I compute some basis functions phi sub m and phi sub n. These are the Laplace-Beltrami eigenfunctions, and so they're standard routines that we can use to compute them, and it's very efficient typically. We don't need too many. Then we have a set of descriptor functions. So I gave an example of Gaussian curvature, which we don't usually use. So there are a few descriptors that have been proposed. Many of them, for example, are based on heat diffusion or different kind of diffusion processes. And we express them in this basis, and this gives us these matrices A and B. So basically, each column of A is the coefficients of one such function in the corresponding basis, and the corresponding column of B is basically the coefficients of a descriptor on N. And then we solve for the optimal functional map by basically solving this least squares problem, where we basically have two terms. The first term is saying, okay, find a map that approximately preserves these descriptor functions, right? So I want to have a correspondence C that, as well as possible, preserves all the description functions that I prescribe. And I have another term that says, find a map that commutes with the Laplace-Beltrami operator. And one question is, like, I think this is, so this is kind of very intuitive. This is slightly less intuitive, but it also kind of makes sense in the sense that, you know, if I take just an arbitrary function, I can do two things. I can first map it and then apply the Laplacian on the target, or I first apply the Laplacian on the source and then map it. And I want this diagram to basically commute. And this is what this term is trying to do. And what we can prove is that if you have a functional map that comes from a point-to-point correspondence, then this term is 0 if and only if the mapping preserves geodesic distances, right? And this is the kind of model that we typically use. So for example, for articulated motion of animals, you know, you would expect geodesic distances to be preserved, and this is precisely what this term is trying to do, okay? And then finally, we can convert it to this to a point-to-point correspondence. So this is the basic pipeline. Okay, so this is something that we proposed in 2012, and I basically, in retrospect, I would say that every single step of this pipeline is suboptimal and or like even wrong. So basically, since then, we've been working a lot on how to improve. So the main 4 steps are still the same, but there are many choices, and I wanted to describe some of them today on how to improve this kind of pipeline. Okay. So today I'll talk about 3 projects if I have time. So first, the one question that also came up yesterday is how can we make functional maps closer to point-to-point maps? Secondly, how can we make them somehow bijective? So one thing that you'll notice is that there's a direction bias. So I'm mapping from the source to the target. But in practice, we're just given a pair of shapes. So why would I prefer one to the other? So can I make them bijective or remove the direction bias? And finally, sometimes you might want to encode some extrinsic information. So all of this pipeline so far only encodes intrinsic information. So for example, geodesic distances. You might also want to encode other quantities, so I'll describe a little bit. And the main kind of goal, at least for geometry processing applications, is that you really want to keep the efficiency, right? So one of the advantages of this pipeline that I just described is that it's very efficient. I mean, it reduces to basically solving a least square system. So what we'd like is basically to have this kind of computational advantage, right? Okay, so the first question is, can we find functional maps that would correspond to pullback by point-to-point map? So I said that every point-to-point correspondence induces a linear transformation between function spaces, but of course the opposite is not true. So you could have a linear transformation between functional spaces that doesn't come from a point-to-point correspondence, right? And one question is when, for example, the opposite is true. And the other question, which actually turns out to be related, but at first sight doesn't seem related, is the following. So remember I wrote down the system where we're basically solving for the C, where we have some descriptor constraints. So I have some coefficients of one descriptor and coefficients of the corresponding descriptor. So suppose that I give you a perfect descriptor, right? So for example, maybe somebody comes in and paints the vertex ID of the shape, right? So if I know how this descriptor is preserved, in principle that should give me the map, right? I have full information. But this linear system actually only gives me k constraints for basically k squared unknowns, right? So somehow I'm not using the full information that's stored in the descriptor, right? So one question is, can we kind of extract more information from a given descriptor while still retaining some kind of least squares efficiency, all right? Okay, so basically the result that we're going to rely on is the result that was mentioned in the first talk yesterday, which basically says the following. So this is, as far as I know, goes back to von Neumann from at least the 30s, maybe even earlier, and basically says that a functional map corresponds to a point-to-point map if and only if it preserves products of functions. So pointwise products, right? So if I have a pair of functions, f and h, I can define their pointwise product, and I can try to map this pointwise product, and that gives me a new function on the target, or I can do the opposite. I can map both f and h separately and then take the product, right? And if this is true for all continuous functions, f and h, then this mapping C has to come from a point-to-point map, okay? So this is kind of, and actually you can, even when you see it, it's not so difficult to at least imagine why this would hold, because a point-to-point correspondence should preserve indicators of regions, right? So if I feed an indicator, it's basically a 0-1 function, the output should be an indicator of some other region, right? And basically if I take an indicator of a region and I just multiply it with itself, so it gives me the square, that's the same indicator of the same region, right? So here basically I would at least expect this to preserve squares, right? And this is exactly what this constraint is encoding. And actually just by this intuition you can more or less, up to some technical constraints, you can more or less prove this result already, okay? So now, how can we use this in our algorithm? So of course, one approach would be to basically say, okay, I'm going to take a whole bunch of different test functions and I'm going to add a constraint to my optimization problem that basically tries to enforce this directly, right? Now, the problem with this approach is twofold. First, it leads to non-convex energy, because now instead of having a single C, so I could take, for example, the left side minus the right side and like take the norm of the difference. But now I have this product of the C's, right? So this is already a non-linear constraint. This makes it much more difficult to optimize. Also, the other problem is that if you want to define pointwise products, you have to basically look on the primal domain. You have to take a function, reconstruct it as its values on the surface, and then take products. So basically this mixes the primal and the spectral domains. So this is kind of highly inefficient. So is there an approach that we can use that still uses this information but somehow is more efficient? So what we propose is actually a very simple version of this idea. Is the following. So suppose that I have some function f which is fixed. Okay, so this is very important. So this function f is fixed, and now I'm defining a linear operator s that takes a function h and just multiplies it with this fixed function f. Okay, so this is just saying that the output of this operator at any point x is just a product of f of x with h of x. This is like a super simple operator, right? So for example, if f was 0, then like a 0 function, then for any function h, this s of h would just be 0, right? But of course, if you take some other fixed function f, you'd have something else. So now here's a slight kind of trick. So remember that we had these descriptor constraints. So we said that there are certain functions that we would expect to be preserved, right? So what we can do is we can construct a multiplicative operator on the source with respect to one descriptor, and we can construct a multiplicative operator on the target with respect to the corresponding descriptor, right? So this is the kth descriptor. And then what we would expect is basically the following. So I think it's easier on the diagram. So what we would expect is the following. So for any function h, if I multiply it pointwise with one descriptor on the source and then map it, should be the same as mapping this function h and then multiplying it with the descriptor on the target. And this gives us this commutativity constraint, right? So basically we start with some descriptor functions, we express multiplication with those descriptor functions as a linear operator, and then we write down this commutativity constraint, okay? And so, so one thing that you can immediately notice is that this constraint is still linear in C, right? We don't have these products of C's. And it also has some nice properties, so just to mention a couple. So first, we can prove that if you have this commutativity with the multiplicative descriptors, and you also have the preservation of the constant function, this implies the old constraints that we had, right? So basically, the constraint that I just described, where you just say like CA equals to B, is actually a direct consequence of this, and this holds both in the primal domain and the spectral domain. And also, what we can prove, and I think this is actually kind of interesting because, it took us like, 4 years to realize this. And in a way, it's kind of obvious, right? I mean, like, you're losing some information from the descriptors. So it's natural to try to express something like this. But I think one of the problems is that our intuition comes from the primal domain, from the spatial domain. And this is kind of encoded in this theorem. So if we have two functions with the same values, then if you express them in the full basis, so just as values on the surface, then for any doubly stochastic matrix, the preservation of the values actually implies this commutativity constraint. Okay? So if we're kind of thinking about correspondences in the domain of points, then these two constraints are equivalent. But if you're writing them in the spectral basis, in a reduced basis, they're not equivalent. And one is strictly stronger than the other. Okay? So here, so basically what we did was we modified this kind of pipeline by adding an extra term by this commutativity. It's still linear in C, or quadratic in C, so basically it's a least squares problem. And what is kind of interesting is that the results that we got are significantly better using the same exact descriptors, right? So here, this plot shows on the x-axis I use some kind of a threshold of an error of the map that we compute with respect to some ground truth map. And on the y-axis is basically the percentage of the correspondences that are within this error. So ideally, I'd like something like this. And here, we have basically the solid lines are using this commutativity constraint, and the lines with the dots don't use it. And what you can see is that if you have many descriptors, then they kind of approach each other, right? Because basically, if you have many kind of good descriptors, then your k-squared linear system is fully determined, so you have already full information. But what's remarkable is that if you have only one or two descriptors, you can still recover a very good map. And in this case, it's actually better than using 100 descriptors written in a different way. Okay? So we can basically take just one or two descriptors and like without modifying anything, just write them in a slightly different way and get a much better map out of this. So this I found quite exciting. So here's an example on a different pair of shapes. Right. So so this was kind of our first let's say contribution or idea in this direction. And now kind of to continue, the second question that I wanted to mention was you know, we have this bias between the source and the target, right? So we're basically mapping from shape M to shape M, and somehow we would like to come up with a problem that doesn't depend on one of these shapes to be the source and one of them to be the target. So one question is, can we somehow remove this bias? And another like closely related question is somehow we have these functional maps, but also we have this functional spaces that have inner products. So what we can do is we can define the adjoint, right? Or basically in the discrete setting is just the transpose. So what we also wanted to answer is there some kind of information encoded in the adjoint, right? Okay, so what this is another work also from this year, where we looked at basically this very, very simple problem where you have a pair of shapes M and N, and you have this functional map from M to N, so it maps functions from M to functions on N. So remember that the adjoint is basically also a linear operator in the opposite direction, and it's defined implicitly, so there shouldn't be a parenthesis, so it's defined implicitly by basically this equation. So for any pair of functions, the inner product of the image of f with respect to any function g should equal to the inner product on M between f and the adjoint of g. And of course you can... Yes, Sobolev inner product, exactly, yes. This is good remark. Right, so this is just a definition of the adjoint. Now, what we do is basically we come up with, we construct two adjoints, one with respect to the L2 norm, and this is kind of a good question of when it actually exists, and another one with respect to the H1, which is just basically defining the inner product by taking the integral of the inner products of the gradients. And in the discrete setting, you can basically express both of them by just some operation with respect to the Laplacian on the two surfaces. And what I think is nice in here is that you can prove that basically the adjoints encode a lot of geometric information. So, you know, the functional map itself, this matrix C, only maps functions, right? In some sense, it's oblivious to the geometry or to the transformation between the spaces, right? It just maps values. But the adjoint actually reflects some geometric quantities. It reflects sort of the distortion induced by this mapping with respect to the inner product. So what you can show is that this map, if a functional map C comes from point-to-point bijection, then this mapping T is area preserving if and only if the inverse is equal to the adjoint, and it's conformal if and only if the inverse is equal to the H1 adjoint. Okay. And how do you use this in an algorithm? So basically what you can do is, you know, so remember that we had some kind of energy that takes a functional map and produces a number, and we try to optimize this energy. So one approach is to say, okay, let's say instead of optimizing for a single functional map from M to N, I'd like to optimize for both a functional map from M to N and another one from N to M, so in the opposite direction, right? If I do this independently and I don't have any coupling, of course I don't gain any information. So one idea would be to introduce an extra coupling term that basically says that if I compose them, then I should get identity. So if I go from M to N and from N to M back, I should get the identity map, right? So this is proposed by Davide and Emanuele in a 3DV paper last year, and I think it's a really, really nice idea. One slight issue with it is that once again, it leads to a non-convex energy, right? So we had this like debate with Michael Bronstein. So he doesn't mind non-convexity. I'm somehow super scared of it. So I try to avoid it completely. So maybe for him it doesn't matter too much. But basically, you know, you see that now you have this coupling term that basically is a product of two functional maps. So somehow we want to avoid this non-convexity term. And here is an image that basically shows that if you just use the regular approach, then what you get is some kind of a map that's not necessarily bijective. But if you use this coupling, then you get, so here the blue parts correspond to points on the surface that don't get any map from the source shape. And if you use this coupling, then you basically get something slightly better. So what we do is we basically replace the coupling with just the, just the product by this adjoint, right? So what we'd like is that the map from M to N should be approximately equal to the adjoint of the map from N to M, right? And similarly, so with respect to the L2, and similarly with respect to the H1. And now, so we solve for both CMN and CNM, and what's nice is once again we have basically a quadratic energy, so it's once again convex. And because it's convex, we can basically get a global minimum of the energy, which also improves also the bijectivity actually of the map that we get in the end. Yes.
Do you understand why it's happening? I mean, you don't have you're not covering these regions. I mean, they don't seem harder than the rest. But,
I think the problem comes from this last step that I'm not, basically today I'm not going to talk too much, is this conversion from a functional map to a point-to-point map. It's basically kind of an error-prone step, and I think if you improve that step, you can easily cover the full shape. It's not part of the map itself. So even if I take a ground truth functional map and convert it to a point-to-point map, it's not going to give me a 100% coverage because there's some loss. But there has been some work, for example, by Emanuele that does a much better job in terms of coverage. So here I'm using some very, very basic approach.
Maybe the descriptors are not good in those regions.
It could also be, yeah.
I think it's the ICP step. You're using the ICP step, right?
Yes, also, yes.
I think it's typical for that.
Yeah, so
But before ICP is actually even worse. So,
yeah.
So Max, I wanted to mention that we also keep the energy quadratic, and we optimize over the manifold of orthogonal matrices.
Right, so it's quadratic on a Stiefel manifold, right? Yeah, so, yeah.
Still.
Yes.
Different kind of convexity. Okay? And so here's some basically, once again, we show some comparison with respect to some baseline, where this adjoint regularizations really helps a lot in terms of the quality. Yes?
I want to clarify notation. What's the meaning of last term? Is that matrix or operator?
So here is a matrix. So for us, all of these are matrices, so I consider them to be like a k by k matrix. And so here the transpose really is the matrix transpose.
The delta is some...
Delta is a matrix which is the basically the spectral representation of the Laplace-Beltrami operator, which basically is just the diagonal matrix of eigenvalues. Okay. All right. Okay. Is there any other questions? Okay. So in the last part, like relatively briefly, so one small thing I wanted to advertise is actually this paper where we talk about this adjoint representation is actually not specific to shape correspondence. We also discuss a few other properties of it. For example, for shape exploration. So can you, like one of the applications there, can you detect regions, for example, that undergo some distortion? And the adjoint actually is quite useful in that kind of scenario. So I'm not talking about that today, but I mean, just in case you're interested. I think this is nice in the sense that it encodes some geometric distortion information. Right? So in the last part, basically, I wanted to describe something that's slightly more ongoing, but is also, I find, very fascinating, is this question of, can we add some kind of extrinsic information to this whole pipeline, right? So so basically, if I look at this kind of term, so even if you look at these, they all try to kind of preserve some notion of distortion that's purely intrinsic. It's either distortion of area or distortion of geodesic distances or angles. But in some cases, you might actually be interested in preserving extrinsic information, right? And actually, another, so I like to think in kind of about the same question from two different points of view. And another point of view is the following. So, in the continuous setting, when you're talking about surfaces, you basically, the fundamental theorem of differential geometry says that we represent surfaces by their first fundamental form, which basically intuitively encodes geodesic, and the second fundamental form, which intuitively encodes curvatures. So one question is, can we kind of come up with some kind of equivalent of this shape representation that would encode both the first and the second fundamental form, but would still do everything in this kind of functional language, right? So can we still kind of translate it in some sense? And this part actually is it turned out not so easy, but so I just want to mention one result in that direction. So remember I said that basically we have this result that a mapping, so a point-to-point mapping is isometric if and only if its functional representation C commutes with the Laplacian, right? So this is, so it preserves geodesic distances if and only if this holds, right? So in some sense, intuitively, the Laplacian encodes fully the geodesic distances. So if I give you the Laplace-Beltrami operator on a surface, you can recover geodesic distances from it. I mean, this is a well-known result, right? So now one question is, can we come up with something else that would be somehow like a Laplacian, but would encode principal curvatures, right? Some extrinsic information.
Shape operator.
Sorry?
Shape operator.
Right. Shape operator is a great idea. Right. Yeah. But one thing that is actually somewhat important to us is that we also want this to be positive definite, right? So this is okay. So one thing that turned out to be useful is the following characterization, which is that basically, if you consider a surface, right, embedded in 3D, and you consider a family of transformations of this surface given by the flow of the surface along the normal, right? So if I basically just take at every point the normal, and then I consider displacement of this point along the normal by a fixed amount, right? And I look at the change in the metric of the surface itself with respect to this offset surface, then you can show that in the limit, as the displacement goes to 0, the change in the metric precisely encodes the second fundamental form, right? Yeah, I think this is actually quite intuitive. So basically, in some sense, in areas where you have a negative curvature, you have contraction of the metric. In positive curvature, you have expansion of the metric. So this is one way to characterize extrinsic information by just looking at the intrinsic information, but on the offset surface. Okay. So what we one approach for using this is the following. So what we'd like is we'd like to have a functional map C that commutes with not the Laplacian, but basically the limit of the difference of basically the derivative of the Laplacian of the surface offset by some fixed amount along the normal, right? So I allow my surface to flow along the normal. I look at the Laplacian of this offset surface, and then I try to take the derivative of this kind of Laplacian on the offset with respect to this offset itself, right? And what we can show, I mean, this is more or less just a direct consequence of the result I just mentioned, is that if this commutativity holds, then the map has to preserve the second fundamental form, okay? So what this means, kind of intuitively, is that the principal curvatures are fully encoded by the Laplacian, but in the normal direction, right? And one small question is, how do you actually formulate this in the discrete setting, because you have to take these derivatives. So I'm not going to go into too much detail, but I mean, just to give you the actual formulas that we use. So we basically define a functional operator E, which is kind of parameterized by this normal, and it's defined implicitly as follows. So for every function f, I want this operator E to basically give me the h1 norm with respect to any function g to be equal to basically the infinitesimal strain tensor of the metric, right? So I know the right-hand side, this is fixed, it doesn't depend on E. I'm trying to find this E that would satisfy this equation, and we can prove that it always exists and it's unique, right? I mean, this is like slightly more technical, but one of the reasons why we do this is that this E can actually be defined for any offset vector field. It doesn't have to be the normal. So for any vector field which tells us how the points are moving, we can define this E operator, okay? And now what we can do specifically for the normal is we can ask for a functional map to basically commute with this normal operator E, okay? And once again, we can show that if this holds, then the correspondence has to preserve the second fundamental form. And to finally kind of characterize, this implies that basically two surfaces are related by rigid motion if and only if the functional map commutes with the Laplacian and also commutes with this normal operator, right? So metric change along the normal encodes the second fundamental form, and the Laplacian encodes the first fundamental form. And I mean, this construction is slightly technical, but this is really just what it's trying to do. So here is just some example where we basically try to introduce this extra constraint into the optimization, And one nice thing, once again, it remains quadratic, right? This is a convex optimization problem because this E is fixed. And somehow this additional operator promotes the preservation of the mean and the principal curvature. And here's an interesting, I think, illustration. So previously, what people have tried to do is to add extrinsic information by using extrinsic descriptors, right? So I said that you can basically add any kind of descriptor or feature that you want, and you say, okay, I'm looking for a functional map that would preserve these features, right? And one kind of feature you could do is, for example, some normal variation around the point. So there are descriptors that are somehow intrinsic. So this shot, for example, that Emmanuel, I think, mentioned yesterday during his talk. So this shot is a kind of a nice descriptor, and it encodes extrinsic information. But one thing is that it encodes it around feature points. So it does quite well. If you look at feature points, they get mapped fairly well. But if you have flat regions, right, where you don't have too much information in terms of like a lot of normal variability, you can have a lot of mistakes. So this descriptor is, I think, works very well when you have some high curvature feature points, but in flat areas, it doesn't work so well. Whereas if you add this normal commutativity, it provides information in some sense everywhere. So we're not specifically saying that, you know, at landmark points or feature points we want to preserve curvature. It's doing it everywhere. And actually, you can even combine the two to get really good results. So we compare basically this normal commutativity with shot, and then we also try to add both of them together. So basically use this descriptor that works well at the feature points, and also this normal commutativity that gives you information everywhere, and kind of together they provide a lot of information. And one thing that I like in this plot is that if you look at basically this part of the plot, you see that this corresponds to the points for which the map has a lot of error, right? So these are like outlier points in the map that you compute, because they're very far from the ground truth. If you just use the descriptors, they work pretty well, but then for some points you're making a lot of errors, right? So in order to have 100% accuracy, you have to go very, very far. But if you use this kind of normal commutativity, it bumps this outlier, so you don't have these like really severe mistakes, which in practice are very, very important. So this is a paper that's now under major revision, but it's also an archive. And just to make a small advertisement, another like application of the same tools, which I'm not going to describe, allows us to do certain things that are quite, I think, interesting from the like graphics point of view. So one thing we do is, for example, intrinsic symmetrization. So if you have a surface and you have some symmetry on it, and you'd like to deform the surface to make it more symmetric without changing the pose. So we can do that by basically finding a displacement field that somehow makes the metric as close as possible with respect to the symmetry without changing the pose. And also we do some deformation transfer. So if I have a source and some different poses of the source, and I have some target, I can basically represent my this displacement as a linear functional operator, and I can transfer it without using point-to-point correspondences. So here we also compare some other techniques. All right, so just to conclude, basically, so I talked basically about this functional maps framework, and one thing that I think is, I don't know, to me is kind of interesting is that often in this field you have like some basic building blocks, and the exact way in which they function is not necessarily optimal. But what you can do is you can kind of modify each building block without modifying the whole framework. And if you're interested, we gave a course recently at SIGGRAPH, and there's a website where a lot of these ideas are mentioned, maybe not the most recent ones. And we also have some code that allows you to play around with some of these techniques if you're interested. Yeah, there's some references. So yeah, thank you.
Great questions.
How do the maps that you reconstruct behave when you're far away from isometric surfaces?
That's a great question. They don't behave very well. I guess it depends what you mean by far away. But if you're really, really far away, I think we don't know how I mean, there are certain scenarios where I think we can do certain things. For example, there's been some approaches using learning that still use functional maps framework, but with learned features, and they can work well in the presence of non-isometric shapes. But there are other problems, like for example, the choice of bases I think is important, and we don't have very good bases that would be resilient to non-isometric deformations. Also, these kinds of constraints don't make sense anymore, right? So I think you know, there's definitely some work to be done. It's, I would say, resilient up to a certain point, but if you're really far, then it doesn't work. Yeah. So if you're trying to map like a giraffe to a horse, it wouldn't work.
One remark. Sobolev space of order one is just the threshold.
Right, that's what you, yeah.
Stops holding, so you must be larger than 1. But of course, if you go to Sobolev space H2, the whole numerics becomes much more involved. But it might be that some numerical inequivalencies are just due to the fact that you are exactly at the Sobolev threshold.
It could be, and I think actually this is a very good remark. And I think, I mean, we discussed briefly yesterday. It also comes up here, for example. There's this question of what is the right norm on this difference. So we have a functional operator, and in practice we typically take like the Frobenius norm, which I think is a really bad idea. So you might be able to do something a little bit better if you're more careful with the kind of space.
Yeah, operator norm between the Sobolev spaces would
right.
be the most natural.
Exactly. So maybe, yeah, so I completely agree.
But that might not be too, I mean, it might be costly numerically.
Yeah.
Basically, you have, so you're introducing extrinsic information twice, right? So in the descriptor and with this term.
Yes.
In your experiments.
You mean here? Yeah.
Did you try with intrinsic descriptors and normal commutativity?
Yes. I think perhaps even this red curve, I mean, there might be intrinsic descriptors in both. I am not entirely sure.
Okay.
But one thing that we've observed is that, for example, if you have articulated motion, right, it's almost rigid, except you have some, you know, parts where you have distortion, like at elbows and so on. And this, in that case, this kind of extrinsic information is very, very useful, actually, because this, like, almost rigidity is not well encoded by purely intrinsic descriptors. If you have significant non-rigidity, like non-local, you know, for example, you have, like, I don't know, tail of a cat or something, then it's a bit less useful.
If you have noisy features matching, may also impair the computation of C, because you assume perfect knowledge of correspondence between the functions.
I actually wouldn't say that. And I mean, I agree with you up to a certain point, but actually, and this is one of the things that I wanted to emphasize in my talk, is that we have also strong regularizers, for example, like, you know, even here, right? But also like with this adjoint and so on. And they can actually help you recover from noisy descriptors up to a certain point, of course. You know, if you have really, really bad descriptors, then. And I think you can probably get away almost without any descriptors, just using these two terms. The only thing is you have to like be careful, especially, for example, if you have symmetries on humans, you might get something that's a mixture of the two. But these, at least in the presence of full information, we can prove that this fully encodes a shape up to rigid motion. Yes?
What happens in the case of partiality?
You should ask him, yeah. I don't know.
What happens in the case of partiality?
There was a great talk yesterday about that.
So it is not purely extrinsic information, this En.
Right.
Because there is the Gauss equation which ties the second fundamental form and the first fundamental form, and zero, which is the curvature of the surrounding space.
Yes,
so
but
you have
well, we take the limit, right? So we actually don't use the displacement. So we really do take the limit here. So yeah, but I mean, yeah, you're right that there's an additional term.
So this is not purely extrinsic. It's
I mean, I agree that there's some kind of interplay, but it like basically it definitely, in the sense that it definitely adds all of the extrinsic information that you might need. So I think that's maybe a more correct thing.
Any more questions? thank the speaker.